Okay guys, let's take a look at today's lesson. So today we're going to be looking at geometric sequences and series. And so we have a few formulas that we need to memorize. Don't make me call you out. We have the sequence formula right here where it's basically a times r to the n minus 1. Okay, this right here. Now that's the formula that we use in Precal. Doesn't necessarily have to look like that. It could be a times r to the n, could be a times r to the n plus 1. Really, it could be anything. And in this formula only, if n is 1, would a be the first term. I just really need to make that clear because that is not always the case. A is not always the first term. And that provides a ton of confusion to students. A is only the first term if it's written like this with the n minus 1 and n starts at 1. That's the only time it's the first term. Okay? So I just want us to make sure we understand that. R is the common ratio. So the common ratio is what you use to multiply each term by to get the next term, right? You probably remember that from last year. We also have an nth partial sum, and so that's this formula right here. This is the nth partial sum. So if I wanted to find like the fifth sum or the fifth partial sum or the 10th partial sum, I would use this formula. This formula requires that you have the first term and that you have r and that you know how many terms. That's basically it. You don't need the last term like you do, in arithmetic sequences and series. When we were working on that, you would need the last term, but not in geometric. You just need to know the first term, the common ratio, and how many terms you're wanting to add up. So this would be our partial sum formula. And lastly, we have the infinite geometric series formula. So this formula right here only works on an infinite series with one particular criteria. You can't just use this formula on any series. I mean, you could plug numbers into it, but it wouldn't have any meaning unless this were true. The absolute value of r has to be less than 1. It has to be. So whatever our common ratio is, the absolute value of it has to be less than 1. Yes? Yes, isn't that so crazy? So it's actually an infinite series, but if the absolute value of r is less than 1, it actually adds to something. You're like, what? I can keep adding an infinite number of terms and it actually adds to something? And it does. It's going to add to whatever number comes out. Basically, it's a limit concept, the limiting concept. It's going to get closer and closer to that particular number until, it just gets closer and closer. It may never become that number, but it is that number. That's what we go with. Yes. Yes, it sure is. Okay, so in this particular formula, a, of course, is my first term over 1 minus r. And that's what we'll use if we have an infinite geometric series that we want to find the sum of whose absolute value of r is less than 1. Okay? We okay? All right, let's move. We have several examples on the next page. Actually takes just a little bit. This lesson is a little bit longer than the normal lesson because there's a lot going on here. So let's start with the first one. So we have the third term of a geometric sequence is 63rd fourths, and the sixth term is 1701 over 32. Find the fifth term. Well, for geometric series, we don't have this cool little formula like we do in arithmetic series where we can find the, in arithmetic we can find the difference, the common difference. We use that. We take the terms over the term numbers, a nice little formula. We really don't have that here. We have to find it with a system of equations. Yes, a system of equations. So I'm going to show you how I do it. I think it's the easiest, quickest way. Do you have to solve the system and do it the way I'm doing it? No, you don't. But I'm just going to show you. There are other ways, but I want to show you what I would typically do. What I would do, so we're going to use that a sub n equals a times r to the n minus 1. We're going to use that standard Precal formula. And what I'm going to do is I'm going to write an equation for each one of these terms. And I'm going to choose to put the sixth term, the term with the largest term number on top, because I'm going to well, we're going to solve this system in a kind of a little bit of a different way. So I'm going to work with the sixth term first. I know the sixth term's value is 1701 over 32, and that's going to be equal to A, which I don't know. I don't know R, but I do know the term number. This is the sixth term, so 6 minus 1 is 5. Okay, so that's my first equation that I'm going to work with. Now I'm actually going to divide the equations. Now we don't usually do that, divide equations to solve a system, but this is basically the best way this works. We're used to adding and subtracting equations and doing substitution. We're not really used to this, but it's certainly a legitimate technique. It's fine to divide equations. We just need to make sure to line the equal signs up. So in the denominator, I'm going to put the third term. So the third term's value is 63/4 equals A times R, and I don't know what R is, but I do know that this is the third term, so 3 minus 1 is 2. Okay, is everybody okay with that system? So I'm going to divide those equations, and in doing so, the A's drop out, right? I get rid of those. And if I'm going to do R to the fifth divided by R squared, what would I be left with? R cubed. I'd have R cubed. And then you're going to have a calculator. Okay, I'm not expecting you to be able to divide those fractions, so you would have a calculator. So we would divide those fractions, and when we divide those fractions, we get 27/8. So now I can solve for R by cube rooting both sides. Right, so the cubed root of 27 is 3 and the cubed root of 8 is 2, so R is actually 3/2. So that's one of my unknowns. My other unknown is A, and I'm going to just sub back into one of those equations to get my A value. I always choose the smallest one just because I would rather work with smaller numbers. So I have 63/4 equals A times 3/2 squared. So then, I'm solving for A. I'd get 9/4. I'd divide both sides by 9/4. Again, you would use a calculator. And when you divide both sides by 9/4, you get, strangely enough, 7. Okay, so we have A and we have R. And now we can write our formula. So A sub n equals 7 times 3/2 to the n minus 1. Alright, now we can find any term we want. They actually want us to find the fifth term. So let's do that. So A sub 5 is going to be 7 times 3/2 to the 5 minus 1. Or, with a calculator, let's see, we get 567 over 16. So as we go through this lesson, I'm going to also show you the non-negotiables for work. Since this unit since we have a calculator, we tend to, sometimes skimp on the work that's shown. So what would I need to see? I need to see, if you're dividing equations, I would need to see this. I need to see your setup. I need to see what R is and what A is. You don't necessarily have to show me plugging in. I just need to know what they are. I need to know our formula, and then you can go to the answer. Okay, those are the things that are non-negotiable. You can show more things as much as you want, but that's non-negotiable. Okay, so let's look at number 2. It says find the sum of the first 5 terms of the geometric sequence. Okay, so we're looking for the sum, so this is a partial sum. Right, this is a partial sum, so this would be the fifth partial sum. The fifth partial sum, we're going to use that partial sum formula, which tells us that A, right, the first term, times, in the numerator we have 1 minus R. Okay, we need to find R. So let's remind ourselves, how do we find R when these are in sequence? Well, we could take the second term over the first term, or we could take the third term over the second term. Whichever. That's what we're looking for. So R is 0.7. So 0.7 to the, let's see, it's the first 5 terms over 1 minus 0.7. Okay. So then we would use our calculator, and we would get to 0.773. Okay, this one, the work is fairly simple. I need the formula and the answer. Okay? That's all you need to show for work on that one. How are we doing? Okay. All right, let's look at number 3. All right, so this is an infinite series. They want us to find the sum of the infinite series. No, we don't have an infinity button on our calculator to do. We're just going to have to work on this. So I would like to rewrite it to make it a little clearer what r is. Well, we know r is not 5. I mean, that's just kind of weird. So do you have to rewrite it? No, I'm just going to rewrite it so that it's clear. Okay, so we're going from 1 to infinity. Okay, so is everybody okay with that rewrite? Okay, see 2's not to any power, it's just a plain old number. 1/5 to the n. Now this is a perfect example of where the number out front could trick us. 2 is not the first term. 2 is not the first term. Why is 2 not the first term? Because we're starting out with an n of 1, right? Yeah, it's going to be 2 times 1/5. If we were starting out with an n of 0, what would our first term be? 2. Okay, so it really matters. It matters a lot. So we really have to pay attention. I encourage you to always plug in to find the first term. Just to double check. Don't just assume that it's this number, because in this case you'd have been completely wrong. Right? So I plug a 1 in, I get 1/5. So my first term is 2/5. Now let's see if our formula would work anyway. I mean, the only way our infinite sum geometric formula will work is if the absolute value of r is less than 1. Is that true for this particular series? That's true, right? So we can use our formula. So our first term is 2/5 over 1 minus r, and r is 1/5. Okay, so I'm not going to go through the arithmetic, but we would add those together, and that would give us 1/2. Okay, we okay with that? Okay. Number 4, I know you had some like this last year, and sometimes these just really confuse students. This like expansion thing. We want to write this as a series. So we want to, a series is things that you add together. So we want to write it as some things that you add together. That's what we're looking for. So this 2.3 really isn't part of the expansion. Do you see how it's just weird, right? Do we have to deal with it? Yes. But it's not really part of the expansion, so I'll write it as a fraction. But it's not really part of the expansion. And the expansion needs at least 3 terms. I mean, that's a thing, right? We need at least 3 terms for the expansion, and this one doesn't count. Poor little 23 tens. I don't want to hurt its feelings, but it doesn't count. It doesn't count as one of the 3. So what I'm doing is it's 5/1. That's the repeating part, right? 5/1. So plus 5/1 over. Now how do I determine what the denominator is? Well, what I do is I look to see what the last, this term, what place value does this have? It's in the thousandths place value. So it's going to be over 1,000. Okay? So then I'm working on this one now. So 51 over, and I look at that place value. Be 100,000. Plus, I need a third one because I need 3 terms, and that poor little guy doesn't count. So 51 over 10 million. Yep. Plus ... Okay, you got to put the plus ... If you don't, then it's finite and it stops. Okay, it doesn't stop, right? They have a ... here. We have one too. It's just going to keep going forever and ever. All right, so we just wrote it as a series. Are we okay with the writing it as a series? Okay, we just wrote it as a series. Now we're going to find the sum of the infinite series. All right, I'm going to deal with this part. Really, that's just a little, it's an attachment. We'll deal with it later. I'm going to deal with the actual expansion of the series that we just did. So to be able to use this formula up here, and so this was our non-negotiable, the formula and the answer. To be able to use this formula, my R value, absolute value R, has to be less than 1. We need to find out what is R. What is R? What do I multiply this by every time to get the next term? 1 over 100, right? And if that doesn't make sense to you, you could, in your calculator, divide this one by this one. I mean, you're going to get 1 over 100. So R is 1 over 100. So I can use this summation formula, right? So the sum is going to be the first term, which is 51 over 1,000, divided by 1 minus R, which is 1 over 100. Okay? Now, you would find a common denominator, right? We would be working through that. So we're going to get 51 over 990. Okay? So that is work that we need to show. So that isn't actually the full sum, though, right? What have we left out? The first term, the 23 tenths. Poor little 23 tenths. We can't forget about them. So the actual sum is 23 tenths plus 51 over 990. No, I don't expect you to do that in your head. You would have a calculator to add those fractions together, and you should get 388 over 165. And so then we would need our final sum, which would be this. Okay, how are we doing? We okay? All right, last one. Actually, these last two problems are they are the where we tie that to calculus. These last two problems, these are called power series. They're a pretty big deal. We're going to be finding the interval of convergence, which we do in calculus of power series. We find the interval of convergence, and we're going to find the sum expressed in terms of x. We're going to do these things, okay? So, of course, in calculus, there's a lot more to it than what we're doing. A lot more to it, but we're just want to know how does it work. What are we doing? How does it work? So, interval of convergence. What in the world is that? First of all, these are geometric series, and we know that this is the only time that the series will converge, right? This is the only time the infinite geometric series will converge, period. So if they're wanting the interval of convergence, what they're wanting us to do is to find R and plug it into that formula and work it out. That's all that they're asking for. The interval of convergence. This is the interval of convergence. Okay? So let's find R. Let me get a little space over here. Come on, you can do it. There we go. Get a little space. So let's find R. So hopefully we're comfortable with finding R, and I don't need to go through that every time, right? So R is going to be negative x plus 2, right? The second one over the first one, you know, that's going to be negative x plus 2. That's our R value. So now we're going to place it in this formula. Why? Because this is when they converge, when the absolute value of R is less than 1. So the absolute value of negative x plus 2 has to be less than 1. So here's where we solve an absolute value inequality, which we've been working with for years, right? Why did we learn how to solve absolute value inequalities? This is why. Because you can't find the interval of convergence if you don't know how to solve an absolute value inequality. So see how everything you've learned is like coming together? So let's change it into what we know it's supposed to look like, right? In order to lift the absolute value bars, do you remember this is a less than or and? Do we remember what we do? We do the negative 1 less than negative x plus 2 less than 1, right? That's our formula. To lift the bars, we put a negative, whatever that is, and then less than. So I really have two inequalities to solve, two different ones. Now some students can solve it like this in a whole. Some students get really troubled with that and need to break them up. So I'm actually going to break them up into two different inequalities. So negative 1 less than negative x plus 2 is one equality I need to solve. The other one is negative x plus 2 is less than 1. Okay, those are the things that I need to solve. So I move the 2 over. It becomes negative 3 less than negative x. Now we know dividing by negatives causes craziness, right? We have to flip the sign. Or what you could do is just take that one over there, right? If I'm going to move the x over there, I'd have to subtract it. You know, it's going to be added, so it will be x is less than 3. Okay, several ways you can deal with that. But x is going to be less than 3. So over here, I have negative x is less than, what is that going to be, negative 1? Or x is bigger than 1. So if x is less than 3 and bigger than 1, I bring it all together, and I have 1 less than x less than 3. This is my interval of convergence. What in the world does that mean? What does it mean? What it means is, if I take a number between 1 and 3 and plug it into this series, it will be a convergent series. I'll get an answer if I add to infinity. That's what it means. I will get an answer. If I add all those terms, you know, with a 2, let's say I put a 2 in here, and I add all those terms, I would get a number. And you can see a 2 actually would, you know, give us a sum of 1. Right, if I put a 2.1, any number between 1 and 3, not including 1 or 3, would cause the series to converge. Okay, and that's part A. So this is part A. Part B is find the sum expressed in terms of x. Well, how are we going to find a sum of an infinite geometric series? We're going to use that formula, right? A over 1 minus r. That's what we're going to do. So S equals A, my first term is 1, over 1 minus r, which was negative x plus 2. So my sum is 1 over, let's see, x minus 1, when I get that all cleaned up. All right. So we've just delved into power series. That's so exciting. We found the interval of convergence, and we found the sum of that power series. Okay, which you did last year in Algebra 2, right? You would have done some of these. You may or may not remember. All right, let's do this next one. So same process. I have to find r. So r is going to be x squared over, x to the 4th over 6 over x squared over 3. So negative x to the 4th over 6 over x squared over 3. I mean, that's how I find r, right? The second term over the first term. I divide it. So what do I get? I get r is negative x squared over 2. That's my r. Okay. Once I find my r, how can I find the interval of convergence? What do? I plug r into the formula. This is the formula for interval of convergence. This is when geometric series converge. This is the only time when geometric series converge. So I take my r and I'm going to put it in that formula. So I have absolute value of negative x squared over 2 less than 1. Okay. So now let's take our absolute value inequality and let's solve it. So negative 1 less than negative x squared over 2 less than 1. What I would like to do is just to multiply everything by 2 to get rid of the fraction. I think it's just easier. Do you have to do that? No. Negative 2 less than negative x squared less than 2. Okay. So now, again, just to help the students that really don't like solving it in one piece, I'm going to split it. So I need to deal with negative x is less than negative x squared. I need to deal with negative x squared is less than 2. Now let's look at this one right here. Negative x squared is less than 2. Is there any time that this would not be true? Can you think of any x that I could put in there that would make this false? No. A negative number is always going to be less than 2, right? So I don't really even need to deal with this one because it's true. And this is an and, right? For an and to work, this and this have to work. So, oh, that's nice. Everything works for that one. Just a really nice little guy, right? Oh, everything works. That's fine. I don't need to work with it. I just need to focus on this one. Okay? Because this one really, okay, everything works. Yay. All right, let's go over here. So I really don't like the negatives, so I'm going to flip the side, switch the sides, because I just don't want to deal with negatives. So what do? No, we don't square root both sides. It's an inequality sign, not an equal sign. So I move everything to one side, and I do sign analysis. I mean, that's what we do when it's not linear. When it's not linear, we do sign analysis. You may or may not remember. So, but where is this 0? How would I find where this 0? I just set it equal to 0 and solve, right? Move the 2 over, square root both sides. Do we see where would it be 0? It would be 0 at negative root 2 and root 2. Right? That's where it would be 0. Now some students were getting confused earlier. I'll just write it out. I'm finding, so I square root both sides and I get plus minus 2. So let's test the signs. If I put a 10 in here, negative 10, I get positive. If I put a 0 in there, I get negative. I'm testing this. If I put a 10, I get positive. So this is only true between negative root 2 and root 2. That is my interval of convergence. This is true. This is negative. I get a negative number between negative root 2 and root 2. So my interval of convergence is negative root 2 less than x less than root 2. That's A. B. What's my sum? Sum is going to be the first term, which is x squared over 3 divided by 1 minus r. And r is negative x squared over 2. Okay, so this is the same problem that we did before. I'm just giving you another example, so hopefully with 2 examples it will make more sense, because I think this is the most complex thing that we're doing, is the power series. Alright, so I find a common denominator, so x squared over 3, so that would be 1 plus that, so I find a common denominator, so I get 2 plus x squared over 2. Right, because in order for me to flip and fix a complex fraction, I have to find the common denominator. Remember that? Sure we do. We're great in algebra in here. So I flip and fix that, and I get my sum to be, let's see, flip, we get 2x squared over 3 times 2 plus x squared. And really there's no need to go, I mean, you can multiply that out if you want to, but it's not necessary. All right. How was our lesson? Are we okay? So I guess non-negotiables here, I suppose I should highlight those. Non-negotiables, I need to see this. Okay, and I need to see this. You can show me all that work in between if you want, that's fine. I need to see the sum. Same here. I need to see this and the sum. Okay? All right.